Why time runs faster for your face, so your face is older than your feet. Not by much, not by anything you'd notice in a mirror. But right now, as you sit there watching this, the top of your head is aging faster than the soles of your shoes. This is not a metaphor. This is not poetry. This is a measured, confirmed, experimentally verified fact about the universe you live in. And it should disturb you. Because if time itself runs at different speeds across your own body, then everything you think you know about what time is, how it works, and why it flows is wrong. I'm Leonard Susskind. I've spent over 50 years thinking about the structure of space-time, and I can tell you with complete confidence that time is not what you think it is. It's not a river. It's not a clock ticking. It's not some cosmic metronome beating the same rhythm everywhere. Time is elastic, time is local. Time depends on where you are and how you're moving, and the differences are not theoretical curiosities locked away in Einstein's equations. They are happening to you right now, inside your body, between your head and your toes. Let me show you exactly what I mean. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, did something extraordinary. They built 2 aluminum-ion clocks, the most precise timekeeping devices ever constructed, accurate to within 1 second in 3.7 billion years. They placed one clock on a table. They raised the other clock just 33 centimeters higher, about a foot. And then they watched. The higher clock ran faster, not by a lot. The difference was about 4 parts in 100 quadrillion. But it was real. It was measurable. It was exactly what Einstein predicted in 1915. The clock that was a foot higher, a foot farther from the center of the Earth, a foot higher in Earth's gravitational field, ticked faster than the one below it. Time itself ran faster at the higher altitude, 33 centimeters less than the length of your arm. And time was already different. Now think about your body. Your head is roughly 1.7 meters above your feet when you're standing. That's 5 times the separation in that experiment. Your head, your brain, your face, they exist at a slightly higher gravitational potential than your feet. And because of that, time runs faster there. Your face ages faster than your feet. Every second of every day since you were born, the cells in your face have experienced slightly more time than the cells in your toes. It's tiny. Over an 80-year lifetime, your head will have aged about 90 billionths of a second more than your feet. That sounds like nothing. And for your body, it is nothing. You'll never feel it. You'll never see it. But here's why it matters enormously. It means time is not universal. It means there is no single clock for the universe. It means the thing you call now, this present moment, is not the same everywhere, not even across the span of your own body. And that changes everything about how you should think about reality. Let me take you back to 1907, because that's when this whole story begins. Einstein had already published special relativity 2 years earlier, in 1905. Special relativity told us something shocking about time. If you move fast, your clock runs slow relative to someone standing still. Time dilation. Most people have heard of it. But in 1907, Einstein was sitting in his office at the patent office in Bern, and he had what he later called the happiest thought of his life. He imagined a person falling off a roof. Not a pleasant image, but bear with me. Einstein realized that a person in free fall doesn't feel gravity. If you're falling, everything around you is falling too. You feel weightless. This is exactly what astronauts experience in orbit. They're not outside gravity. Earth's gravity is pulling on them constantly. They feel weightless because they and their spacecraft are falling together around the Earth. Einstein saw something profound in this. If a person in free fall can't tell whether they're in a gravitational field or floating in empty space, then gravity and acceleration must be equivalent. This is the equivalence principle, and it's the foundation of everything I'm about to tell you. The equivalence principle says that standing on the surface of the Earth, feeling gravity pulling you down, is physically identical to standing in a rocket ship accelerating upward at 1g. There is no experiment you can do inside a sealed room to tell the difference. None. The physics is identical. Now here's where it gets deep. Special relativity already told us that acceleration affects time. If you accelerate, clocks at different positions in your accelerating frame tick at different rates. Clocks in the direction of acceleration, the front of the rocket, tick faster. Clocks opposite to the acceleration, the back of the rocket, tick slower. And because of the equivalence principle, gravity must do the same thing. Clocks higher in a gravitational field must tick faster than clocks lower in a gravitational field. This isn't something Einstein guessed. It's something he derived from pure logic. From the equivalence principle and special relativity, gravitational time dilation follows as an absolute mathematical certainty. And in 1915, when Einstein completed general relativity, the full theory of gravity, this result was embedded at its very core. Gravity is not a force pulling you down. Gravity is the curvature of space-time, and that curvature means time runs differently at different heights. This is not a small effect that only matters for exotic physics. This is the reason your GPS works. Let me tell you about GPS because it's the most everyday, mundane practical proof that your face ages faster than your feet. The global positioning system relies on a constellation of 24 satellites orbiting Earth at about 2,200 kilometers altitude. Each satellite carries an atomic clock. Your phone picks up signals from at least 4 of these satellites, and by comparing the arrival times of the signals, it calculates your position. For this to work, the clocks on the satellites need to be incredibly accurate. If they drift by even a microsecond, your position could be off by 300 meters. Now here's the problem. Those satellite clocks are 2,200 kilometers above the Earth's surface. They're much higher in Earth's gravitational field than you are. And because of gravitational time dilation, they tick faster. How much faster? About 45 microseconds per day, faster than clocks on the ground. 45 microseconds. That doesn't sound like much, but in GPS terms, it's catastrophic. 45 microseconds of clock drift per day would introduce a position error of about 13.5 kilometers per day. After a week, your GPS would think you're in a different city. After a month, a different country. So the GPS system corrects for this. The satellite clocks are deliberately set to tick slightly slower before launch, so that when they reach orbit and time speeds up for them, they'll match the rate of clocks on the ground. This is not optional. Without the general relativistic correction, GPS would be useless within hours. Every time you use your phone to navigate, every time you check your location on a map, you are relying on the fact that time runs at different rates at different heights. You are using gravitational time dilation. Einstein's 1915 theory of curved spacetime every single day, and you don't even know it. But GPS is just the beginning. The implications go much, much deeper. Here's something that should really bother you. If time runs faster higher up and slower lower down, then what does it mean for time to pass at all? Think about it carefully. You're standing on the ground. Your feet are slightly deeper in Earth's gravitational well than your head. Time at your feet is running slightly slower. Now imagine you could zoom in. Imagine you could measure the flow of time at every point in your body. Your knees experience a slightly different rate of time than your waist. Your waist a slightly different rate than your chest. Your chest a slightly different rate than your head. There isn't one time flowing through you. There are infinitely many times, one for each point in space, each ticking at its own rate determined by the local gravitational field. This is what general relativity actually says. There is no global time. There is no universal clock. There is only local time, what physicists call proper time, the time measured by a clock at a specific location. And every location has its own clock running at its own rate. Now, I want you to really sit with that for a moment, because we all walk around with this deep, instinctive sense that there is a time, one time, flowing forward, carrying us all along together. The same time for me and for you and for the astronaut on the space station and for someone standing on the surface of a neutron star. But that's wrong, completely wrong. Each of those people has their own proper time, their own clock, their own rate of aging, and none of them agree. They're not even close to agreeing in extreme gravitational environments. And this isn't because the clocks are broken. It's because time itself is genuinely different. Let me take this further, because the effect gets spectacularly dramatic when gravity gets strong. Near a black hole, gravitational time dilation goes berserk. A black hole is an object so massive with gravity so intense that space-time curves to an extreme degree. The event horizon, the boundary of the black hole, is the point where the gravitational time dilation factor becomes infinite. Infinite. Let me tell you what that means. Imagine you're watching a friend fall toward a black hole. You're at a safe distance, far away. Your friend is falling in. From your perspective, something bizarre happens. As your friend approaches the event horizon, they appear to slow down. Their movements become sluggish. Their clock, which you can somehow observe, ticks slower and slower. the light from their body gets stretched to longer and longer wavelengths, shifting from visible to infrared to microwave to radio. They get dimmer and redder. And they never actually cross the event horizon. Not from your perspective. They just get closer and closer, moving slower and slower, their image fading, their clock nearly stopped, frozen at the edge of the black hole for eternity. From your friend's perspective, however, things are completely different. They cross the event horizon in a finite amount of their proper time. Nothing special happens at the crossing, at least not locally. They sail right through. But then they're inside the black hole, and the singularity at the center is no longer a place in space. It's a moment in time, a moment in their future that they cannot avoid. Think about what this means. The same event, your friend crossing the event horizon, takes finite time in one frame and infinite time in another. This isn't a matter of perspective in the casual sense. This is a fundamental disagreement about the flow of time. You and your friend will never agree on when or even whether the crossing happened. Time has become so warped, so twisted by gravity, that it no longer provides a shared framework for reality. And this is the same physics, the exact same physics, that makes your face age faster than your feet. The difference is only one of degree. Near Earth's surface, the effect is tiny. Near a black hole, it's enormous. But the principle is identical. Gravity warps time. Deeper in the gravitational field, time runs slower. Higher up, time runs faster. The effect is continuous, and it is everywhere. Now let me connect this to something even more unsettling. If time runs at different rates at different places, then the concept of now becomes deeply problematic. In everyday life, you think of now as a single instant shared by everyone. Right now, at this very moment, everything that exists is happening simultaneously. Your friend in Tokyo, the astronaut on the space station, the rover on Mars, all experiencing the same now. But special relativity already destroyed this idea. Simultaneity is relative. Two events that are simultaneous for one observer are not simultaneous for another observer moving at a different velocity. General relativity makes it even worse. In a curved space-time, you cannot even define a consistent global now. There's no way to slice the four-dimensional space-time into universal moments of time that everyone agrees on. Your now is yours. My now is mine. And they don't have to match. The universe doesn't have a master clock. It doesn't have a universal present moment marching forward into the future. All it has is a four-dimensional structure, space-time, with events located at various points, and each point has its own local rate of time. Here's where people usually push back. They say, okay, Lenny, but the effects are so tiny, billionths of a second over a lifetime between my head and my feet, who cares? Why does it matter? It matters because tiny effects reveal fundamental truths. The fact that the effect is small near Earth's surface is an accident of our environment. We happen to live on a planet with relatively weak gravity. We happen to be far from any black holes or neutron stars. We happen to live in a gentle, quiet corner of space-time where the curvature is so mild that Newtonian physics works perfectly well for everyday life. But the underlying reality is general relativistic. The underlying reality is that space-time is curved and time is local. We just don't notice because we're swimming in such a shallow gravitational pool. It's like a fish in a pond that's so calm, so still, that the fish thinks water has no current. But put that fish in a river and suddenly the current is obvious. Our gravitational field is the still pond. A neutron star or a black hole is the river. The physics is the same, we just don't feel it. And actually, we do feel it in a way. Every aspect of physics that involves energy levels, quantum transitions, the behavior of atoms and molecules, all of it is affected by the local flow of time. When an atom emits light, the frequency of that light depends on the local rate of time. An atom on the surface of a white dwarf, where gravity is about 100,000 times stronger than on Earth, emits light at a slightly lower frequency than the same atom on Earth. The light is redshifted. This is called gravitational redshift, and it's been measured. It was first confirmed in 1959 by Pound and Rebka in a beautiful experiment at Harvard. They sent gamma rays up a 22.5-meter tower and measured the change in frequency. The gamma rays lost energy climbing out of Earth's gravitational field. Their frequency shifted by exactly the amount general relativity predicted. 2 parts in a million billion, tiny, but real, and exactly what Einstein said would happen 44 years earlier. The universe was listening to Einstein's equations with astonishing fidelity. Let me talk about something that I think most people will find genuinely mind-bending. Time dilation is not just gravitational, it also comes from motion. Special relativity, Einstein's 1905 theory, tells us that moving clocks run slow. If you travel fast relative to me, your clock runs slower than mine. The faster you go, the more your clock slows down. At the speed of light, time stops completely. This is called velocity time dilation, and it's just as real as gravitational time dilation. And here's the remarkable thing. These two effects are related. They're both manifestations of the same underlying geometry. Space-time has a structure described by what we call the metric, a mathematical object that tells you how distances and time intervals are measured at every point. In flat space-time, far from any gravity, the metric is simple, and the only time dilation comes from relative motion. In curved space-time, near a massive object, the metric is warped, and you get gravitational time dilation on top of velocity effects. The GPS satellites actually experience both. Gravitational time dilation makes their clocks run faster because they're higher up. Velocity time dilation makes their clocks run slower because they're moving at about 14,000 kilometers per hour relative to the ground. The two effects partially cancel, but the gravitational effect wins. The net result is that the satellite clocks gain about 38 microseconds per day compared to ground clocks. This is real measured, corrected for daily. Now here's a thought experiment that I want you to really think about because it gets at the heart of what time dilation means for your existence. Imagine you have a twin, identical twin, born at the same moment. You stay on Earth. Your twin gets in a spaceship and travels at 99% the speed of light to a star 10 light years away and back. By your clock on Earth, the trip takes a little over 20 years. You age 20 years, you're older, you have gray hair, you've lived 2 decades of experiences. Your twin returns, and when they step off the ship, they've aged less than 3 years. They look almost the same as when they left. This is the twin paradox. It's not a paradox at all, actually. It's a straightforward prediction of special relativity, confirmed by every experiment ever done. Ones produced in the upper atmosphere by cosmic rays survive far longer than they should because they're moving at nearly the speed of light, and their internal clocks run slow. We see this every day in particle physics. The twin who traveled really does age less. But here's the question that should unsettle you. Which twin experienced more time? The answer is obvious. You did. You experienced 20 years. Your twin experienced less than 3. But both of you were conscious. Both of you experienced every moment of your respective journeys. Your twin didn't feel time passing slowly. From their perspective, everything was normal. They ate meals. They read books. They experienced a perfectly normal 3 years. It's just that the universe gave them fewer seconds. The universe was stingy with their time, and this is the deep truth about time dilation. It's not that one clock is wrong and the other is right. It's not that one twin is aging correctly and the other isn't. Both are aging correctly according to their local flow of time. But time itself is different along different paths through space-time. Some paths have more time, some paths have less. Your world line through space-time, the specific path you trace from birth to death, determines how much time you experience. And different paths give different amounts. That's not a metaphor. That's the geometry of space-time. Let me bring this back to your face and your feet, because I don't want you to think this is just about spaceships and black holes. Your face and your feet are on different paths through space-time. Slightly different paths because they're at different heights in Earth's gravitational field. Your face follows a path where time runs a tiny bit faster. Your feet follow a path where time runs a tiny bit slower. Over a lifetime, the difference is negligible for any biological purpose. But the physics doesn't care about biological purposes. The physics says time is different. And if you had a clock precise enough, an atomic clock like the ones at Nest, you could measure the difference in real time. You could watch the clock at your head tick faster than the clock at your feet, and you'd see that the universe doesn't treat every part of you equally. The universe plays favorites with time. Now I want to push this even further because there's a direction this leads that most physicists don't talk about publicly, but it's been keeping me up at night for years. If time runs at different rates at different points in a gravitational field, and if this effect becomes extreme near black holes and neutron stars, then what is time, really? Fundamentally, what is it? In Newtonian physics, time was absolute, a universal backdrop against which everything happens. Newton himself wrote that absolute true, and mathematical time of itself and from its own nature flows equally without relation to anything external. That was the view for 200 years. It was wrong. Einstein showed that time is not absolute. It's part of the fabric of space-time. It's affected by mass and energy. It curves and stretches and contracts. Time is dynamic. Time is responsive. Time is physical. But if time is physical, if it can be affected by the arrangement of matter and energy, then time is not fundamental. It's emergent. It arises from something deeper. And here's where modern theoretical physics gets really speculative and really interesting. In many approaches to quantum gravity, string theory, loop quantum gravity, causal set theory, time as we know it is not fundamental. It emerges from more primitive structures, just as temperature emerges from the random motion of molecules. Temperature isn't a fundamental property of individual atoms. It's a statistical property of large collections of atoms. Similarly, time might not be a fundamental property of the universe at the deepest level. It might be a statistical property, an average, an approximation that works extremely well on the scales we inhabit, but breaks down at the Planck scale at energies and distances so extreme that space-time itself becomes something else entirely. If this is true, and I think it probably is, then the time dilation between your face and your feet is a clue, a tiny, almost imperceptible clue about the deepest structure of reality. It's telling you that time is not what you think. It's not a stage. It's not a river. It's not a metronome. It's a feature of the geometry of space-time, which is itself a feature of the distribution of energy and matter, which is itself probably a feature of something even more fundamental that we don't yet understand. There's one more thing I want to tell you, and it's perhaps the most profound implication of all this. If time is local, if every point in space-time has its own clock running at its own rate, then the question, how old is the universe, doesn't have a simple answer. We say the universe is 13.8 billion years old, but 13.8 billion years by whose clock? The conventional answer is cosmic time, the time measured by a hypothetical observer at rest relative to the cosmic microwave background radiation in a region of average density, far from any significant gravitational fields. And by that clock, yes, 13.8 billion years. But a clock sitting near a massive black hole, since the beginning of the universe, would have measured far less time. A clock in the void between galaxy clusters, where gravity is weaker, would have measured slightly more. The age of the universe depends on the path through space-time along which you measure. There is no single definitive age, just as there is no single definitive now. This is not a technicality. This is fundamental. The universe doesn't have a built-in clock. It doesn't have a master timeline. Each world line, each path through the four-dimensional structure accumulates its own proper time, and that's the only time that's physically meaningful. The time on your clock, the time along your path, your time. And this brings me to something deeply personal. When I was younger, I thought of time as something that happened to me, something external, an invisible current carrying me from the past into the future, whether I liked it or not. I had no control over it. Nobody did. Time just was. But general relativity taught me something different. Time is not something that happens to you. Time is a property of the path you take through space-time, and different paths give different amounts of time. In principle, you have some control over how much time you experience. If you want to age more slowly, get closer to a massive object, or move faster. If you want to age more quickly, move away from massive objects. Sit still. Your face ages faster than your feet because your face is taking a slightly different path through space-time than your feet. It's a path with more proper time. And this is true for every aspect of your life. Every step you take, every flight you catch, every building you climb changes your path through space-time by some imperceptible amount, changes how much time you experience relative to someone else. Now, you might ask, does any of this have practical consequences beyond GPS? The answer is yes, increasingly so. As our technology becomes more precise, relativistic time effects become more important. Particle accelerators, satellite communications, financial trading systems, where microseconds matter, gravitational wave detectors like IGO, which work by measuring space-time distortions smaller than a proton. All of these are affected by the same physics that makes your face age faster than your feet. And as we push toward quantum computing and quantum communication, where timing precision at the attosecond level becomes critical, relativistic time effects will become not just relevant, but dominant. The future of technology is relativistic. We are leaving the Newtonian world behind and entering a world where Einstein's curved spacetime is not an exotic curiosity, but an engineering constraint. But for me, the most important thing about all of this isn't the technology. It's what it tells us about the nature of reality. We live inside a universe where time is not uniform, where different parts of the same room experience time at different rates, where the concept of now is fuzzy and observer dependent, where the distinction between past, present, and future is not as sharp as our experience suggests. This is the universe Einstein revealed to us in 1915, and that a century of experiments has confirmed beyond any reasonable doubt. Your face ages faster than your feet. It's a fact. A tiny, wonderful, deeply strange fact. And behind it lies the entire architecture of spacetime, the curvature of the universe, the interplay of mass and energy and geometry that governs everything from the GPS in your pocket to the light escaping from a black hole to the expansion of the cosmos itself. When I look in the mirror in the morning, I think about this sometimes. I think about the fact that my face has experienced ever so slightly more time than my feet, that every atom in my head has lived through a few extra nanoseconds compared to every atom in my toes. It's meaningless biologically, but it's profound physically. It means the universe treats different parts of space differently. It means time is geometry. It means reality is stranger, more subtle, more beautiful than any of us have the intuition to grasp without the mathematics to guide us. I've spent 50 years following those mathematics, and they keep leading me to places I never expected. The discovery that time runs faster for your face is one of the smallest discoveries in physics, but it might be one of the most important, because it forces you to confront a truth about the universe that you cannot unsee once you've seen it. Time is not what you think. It never was. And the proof is happening right now, inside your body, between your head and your feet, in the quiet, invisible, relentless geometry of space-time that you carry with you everywhere you go and never ever notice. Think about that tonight when you lie down. Think about the fact that the moment you go horizontal, you equalize the gravitational time dilation across your body. Your head and your feet are suddenly at the same height, the same gravitational potential. For the first time all day, every part of you is aging at the same rate. And when you stand up tomorrow morning, the asymmetry begins again. Your face starts pulling ahead, gaining time, aging ever so slightly faster, day after day, year after year for your entire life, and there's nothing you can do about it, because that's what space-time does, that's what gravity does, that's what reality does when you're not paying attention. And even when you are, thank you for listening. Go stand on your head for a while. Your feet could use the extra time.